Hello, and welcome to Physics at Night. I am so glad you are here. Whether you're lying down in bed with the lights dimmed low, slowly melting into your pillow, or curled on the couch, letting your mind float like a leaf on still water, this space is for you. Tonight, we begin something quietly astonishing. We're going to look at the invisible stage upon which your entire life is played. We're going to ask a question that seems too simple to ask until you really think about it. We're going to ask, where are we? And when are we? We're going to talk about space-time, but not the chalkboard equations you might remember from school. We're going to talk about the fabric of reality. We're going to explore why the room you're sitting in and the minutes ticking by on your phone are actually made of the same shimmering stuff. The story of space-time isn't just about gravity and black holes. It is about connection. It is the geometry of how we touch the universe and how the universe touches us back. It is about finding out that the here and the now are not separate islands, but a single, beautiful ocean. Now, I should gently warn you, this concept is slippery. It may soothe you so well you won't hear the end, but if it keeps your mind glowing a bit too long, I promise that even wakefulness can be restful when filled with wonder. If you find peace in this moment, I'd be grateful if you gave this video a quiet like, and maybe subscribe for more dreamy science. And if you're comfortable, I'd love to know where you're listening from and what time it is there. Your words light up a map of bedtime from around the world, a constellation of rest. As always, this story is for relaxation and gentle education only. It is not a substitute for medical advice or professional care. Just a safe harbour to fall asleep with curiosity. Now, let's begin. Open your mind to the room around you. You feel like you are existing in two different worlds at once. First, there is space. Space feels like a box. It is the distance from your head to the ceiling. It is the miles between your home and the ocean. It feels open. It feels like a place where you have freedom. You can walk left, or you can walk right. You can go to the store, and you can come back. Space allows you to return. And then there is time. Time feels different. Time feels like a river. It flows in only one direction, from the past, through the present, toward the future. It feels rigid. It feels unstoppable. You cannot go back to this morning. You cannot revisit the moment you fell asleep last night. Time drags you forward, whether you walk or stand still. For thousands of years, we believed this feeling was the absolute truth. We thought space was the stage and time was the clock on the wall. We thought they were separate containers. But while you lie there, apparently safe in your box of space and your river of time, the universe is whispering a different secret. Einstein taught us that this separation is an illusion. It sounds impossible, but feel it with me instead. Imagine taking the threads of space, the up and down, the left and right, and weaving them together with the thread of time. You get a fabric, a single, continuous, four-dimensional fabric. That is where we are going in this series. We're going to stop seeing the world as a place where things happen over time. We're going to see the universe as a block of space-time. This isn't just theoretical physics. It is a new way of seeing yourself. It means that you are not just a traveller moving through the world. You are a shape in the fabric. So take a deep breath, drop your shoulders, and let's prepare to explore the geometry of existence. Enough thinking. Let's begin by stripping away the world. I want you to imagine that we can turn off the universe layer by layer. First, we turn off the matter. Imagine the walls of your room dissolving into mist. The bed beneath you fades away. The floor vanishes. The roof lifts off and disappears. Outside, the ground melts. The oceans evaporate. The mountains turn to smoke. Even the earth itself, the sun, the moon, and all the billions of stars in the Milky Way, they all blink out. We are left with nothing but darkness, a vast, infinite, empty void. Now, ask yourself a question. In this total emptiness, is there anything left? Our common sense tells us, yes. We feel that even though the things are gone, the places where the things used to be are still there. The here where you are lying is still here. The there where the moon was is still there. We imagine a ghostly grid left behind, a giant, invisible scaffolding that holds the universe together. We imagine that if we had a ruler, we could still measure the distance from one point in the darkness to another. This is what we call space. To our minds, space is the stage. It is the rigid, silent, eternal theatre where the drama of the universe happens. It doesn't do anything. It doesn't move. It doesn't change. It just sits there, waiting to be filled. It has 3 dimensions. You can go up and down. You can go left and right. You can go forward and backward. It feels solid. It feels like a container. But now, think about the other thing. In this empty void, with no stars and no planets, is there still time? Again, our intuition screams, yes. We imagine that even in the dark, a clock is ticking somewhere. Tick, tock, tick, tock. 1 second follows another. The moment now is constantly slipping into the past, and a new future is constantly arriving. We imagine this time as a master clock that sits outside the universe. We imagine that it ticks at the exact same rate for every corner of the emptiness. A second here in the dark is the same as a second a billion miles away. This is the Newtonian view of reality. Isaac Newton, the genius who figured out gravity, told us that space and time were absolute. He said space was a fixed box. He said time was a flowing river. And most importantly, he said they never touched each other. He believed that what you do in space has absolutely no effect on time. You could run as fast as you want through the dark. You could spin in circles. You could teleport from one side of the universe to the other, and the master clock would just keep ticking, steady and indifferent. For 300 years, we lived inside this idea. It feels safe. It keeps our lives organized. We treat space and time as 2 completely different ingredients in the recipe of existence. If you agree to meet a friend for coffee, you have to give them 2 pieces of information. You have to give them a location, space. Meet me at the cafe on Main Street. And you have to give them a moment, time. Meet me at 2 p.m. If you get the space wrong, you are waiting at the wrong cafe. If you get the time wrong, you're waiting at the right cafe, but all alone. They seem like separate coordinates, independent variables, but tonight we're going to break this intuition, because there is a crack in this picture, a tiny, subtle flaw that Newton didn't see. The flaw comes from light. As we learned in our previous nights together, light has a speed limit. It travels at a specific speed, and nothing can go faster. This seems like a detail about light, but it is actually a detail about the container. Think about this. If space and time are separate, then speed shouldn't matter. If I run faster and faster through space, the clock of time should ignore me. But the universe doesn't work that way. The universe has a rule that says the speed of light must be the same for everyone. And to keep that rule, the universe has to do something impossible. It has to stitch the box and the river together. It turns out, you cannot move through space without stealing from time, and you cannot move through time without being anchored in space. They are not two things. They are one thing. I want you to try to visualize a new shape. Don't see a 3D box anymore. And don't see a 1D timeline. See a 4-dimensional block. We call this Spacetime. In Spacetime, up and down are directions, but future and past are also just directions. The difference is, we can turn our bodies to face left or right, but we are physically stuck facing future. We are like passengers on a train that is locked on a track. We're hurtling down the future track at full speed. We call this aging. We call this living. But, and here is the magic, the tracks can bend. If you start moving through space, if you get up and walk across the room, you're actually tilting your train slightly. You're diverting some of your energy away from the future direction and putting it into the space direction. Because you have changed direction in the 4D fabric, you're no longer moving toward the future at the same speed as the person sitting still. Your clock ticks differently. Your path is different. You're not just a person in a room. You're a geometric line, threading your way through a 4-dimensional crystal. Physics calls this line your world line. Your world line started the moment you were born. It is a long, winding snake that twists through the fabric of the universe. Every time you sleep, the line goes straight up toward the future. Every time you travel, the line tilts sideways through space. Every time you return home, the line curves back. And you are not alone. The universe is a tangled web of these lines. The world line of the Earth spirals around the world line of the Sun. The world line of your coffee cup runs parallel to yours while you hold it, and then splits away when you set it down. When we look at reality this way, the emptiness we imagined at the beginning isn't empty at all. It is a fabric. It is a substance. It can stretch. It can wobble. It can tear. And most amazingly, it can curve. When we feel gravity pulling us down into the mattress, we're not feeling a force. We're feeling the fabric of space-time bending underneath the weight of the Earth, and our bodies sliding down the slope. So, the answer to our quiet question is this. Space and time are not a stage and a clock. They are a landscape. And for the rest of this journey, we're going to explore that landscape. We're going to climb the hills of gravity. We're going to slide into the valleys of black holes. And we're going to look at the horizon of the speed of light. But first, we have to understand the old map before we can appreciate the new one. We have to understand what we thought space was, to understand why we were wrong. In the first chapter, we opened a door. We peered through it and saw a strange new world where space and time were melted together into a single block. But tonight, before we step through that door, I want to close it. I want to stay on this side of the door for a little while longer. I want to stay in the world of common sense, the world that feels familiar, the world that your brain was built to understand. Tonight, we're going to look at space. Not space-time, just space. The good, old-fashioned, three-dimensional emptiness that you're sitting in right now. I want you to become very aware of the room you're in. Keep your eyes closed, but visualize the walls, visualize the ceiling, visualize the floor. Now, imagine we begin to empty the room. First, we take out the furniture. The bed, the chair, the lamp, they dissolve. Then, we take out the air. The molecules of nitrogen and oxygen drift away, leaving a perfect vacuum. Then we take out the light. We turn off the sun. We banish every single photon. Finally, we take out you. What is left? Our intuition gives us a very strong answer. We feel that there is a ghost room left behind. The walls are gone, but the place where the walls used to be is still there. The distance from the left side to the right side is still exactly the same, even though there is nothing there to measure it. We imagine a ghostly scaffolding, a silent, invisible grid that holds the potential for a room. This is the classical view of space. It is the view that humanity held for thousands of years. It was codified by the Greek mathematician Euclid, and later cemented into physics by Isaac Newton. To Newton, space was the absolute container. Think about that word. Container. A container is passive. If you have a cardboard box, you can put books in it. You can put pillows in it. You can fill it with water. You can leave it empty. Does the box care? No. Does the box change shape depending on what you put inside? No. The box is rigid. It is separate from its contents. This is how we feel about the universe. We imagine the universe is just a really, really big box, an infinite box. We imagine that you can draw a grid, like a 3D graph paper, extending out from your chest in all directions. The x-axis goes left and right forever. The y-axis goes up and down forever. The z-axis goes forward and backward forever. And this grid is made of iron. It is unshakable. It doesn't matter if a star explodes. It doesn't matter if a black hole spins. It doesn't matter if you run, jump, or sleep. The grid lines remain perfectly straight, perfectly parallel, and perfectly still. This idea of space gives us a sense of profound stability. It anchors us. It tells us that distance is a real objective thing. If you take a ruler and measure the length of your bed, that is a fact. If an alien flies past Earth at the speed of light and measures your bed, we expect him to get the same number. If a ghost measures your bed, he gets the same number. A meter is a meter is a meter. Anywhere in the universe, any time in history. This is the geometry of comfort. It is the geometry of flat space. In flat space, parallel lines never meet. If you shine two laser beams perfectly parallel to each other, they will travel to the end of the universe and never touch. In flat space, the angles of a triangle always add up to 180 degrees. In flat space, the shortest distance between 2 points is always a straight line. This feels so obvious that it doesn't even feel like physics. It just feels like truth. But why do we see it this way? We see it this way because we are small and we are slow. We evolved on the African savanna. We needed to throw spears. We needed to gauge the distance to a predator. We needed to navigate the landscape. For a human being, the world is flat. The world is rigid. If you throw a spear, the space doesn't curve around it. The air moves, but the place stays still. Our brains are hardwired to build this Euclidean map. It is a survival mechanism. We need to know where things are. We need a coordinate system that doesn't wobble. So we project this map onto the entire cosmos. We look up at the stars and we imagine they are just distant coordinates on the same grid that governs our living room. We imagine that if we had a long enough tape measure, we could stretch it from here to the Orion Nebula and pull it tight and get a definitive number. This view treats space as the background. It is the silent stage upon which the drama of the universe plays out. Stars are the actors. Planets are the props. Light is the spotlight. But the stage The stage is just the floor. It doesn't have lines. It doesn't have emotions. It doesn't participate in the play. It is simply the void, the emptiness, the nothingness that sits between the somethingness. But there is a philosophical problem here. A problem that bothered the great thinkers even before Einstein. If space is truly nothing, how can it have properties? How can nothing have a size? How can nothing be flat? How can nothing keep two planets apart? There was a famous debate between Isaac Newton and another genius named Gottfried Wilhelm Leibniz. Newton said, "Space is real. It is a thing. It is like a ghostly substance that fills the void." Leibniz said, "No, space is not a thing. Space is just the relationship between objects. If you take away the objects, space disappears too. It's just a way of saying this is next to that." It's a deep question. Is the distance between two stars a physical object? Or is it just a concept in our minds? Newton won the argument. For 300 years, physics followed Newton. We accepted that space was a thing, but we accepted that it was a thing that does nothing. It is a paradox. It is the invisible, untouchable, unchangeable skeleton of reality. So, as you lie there tonight, feel the space around you. Feel the distance from your ear to the wall. Feel the gap between your fingers. Feel the vast, silent miles of air above your roof. In this classical view, you're a tiny speck floating in a vast, infinite, static cathedral. The pillars of this cathedral are straight. The floor is level. The ceiling is infinite. It is a cold picture, but it is a calm one. It suggests that the universe makes sense. It suggests that structure is permanent. It suggests that no matter what happens to you, the place where you are will always be there. This is the illusion of the box. It is the illusion of stability. But as we will learn, stability is not the same as reality. We're going to find out that the pillars can bend. We're going to find out that the floor can drop out from under us. We're going to find out that this nothing is actually the most powerful something in the universe. But to understand the twisting of the fabric, we first have to understand the other thread. We've looked at the box. Now we must look at the river. We've explored the illusion of space. Now we must explore the illusion of time. We sat inside the empty box. We explored the illusion of space, the rigid, silent stage that we believe surrounds us. We found comfort in its stability. We found comfort in the idea that here is a permanent place. But a stage is useless without a play. A box is meaningless unless something moves inside it. And for things to move, for things to change, for things to happen, we need the second ingredient. Tonight, we must look at the most mysterious, the most intimate, and the most tyrant force in our lives. We must look at time. I want you to close your eyes again. We've emptied the room of furniture. We've emptied it of air. We've emptied it of light. But there is one thing we cannot empty the room of. Listen to the silence. Somewhere in your house, a refrigerator hums. Outside, a car passes. Inside your chest, your heart beats. Thump, 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 thump. Even in the stillness, something is flowing. Something is dragging you from the moment you just experienced into the moment you are about to experience. This is the intuitive view of time. If space is a box, then time is a river. This is the oldest metaphor in human history. The Greek philosopher Heraclitus said, "No man ever steps in the same river twice, because it is not the same river, and he is not the same man." This view of time feels liquid. It feels continuous. It pours over us. washing away the past and carrying us relentlessly toward the future. Unlike space, time has an agenda. Think about the difference. In space, you have freedom. You can walk north. If you don't like the north, you can turn around and walk south. You can correct your mistakes. You can revisit your favorite places. Space is symmetric. Left is just the mirror image of right. But time has no symmetry. Time is an arrow. It points in only one direction, forward. You cannot turn around. You cannot revisit the breakfast you ate this morning. You cannot go back to tell your younger self to be brave. You cannot undo a mistake. The past is a locked door. The key has been thrown away, and the future is a fog. We're rushing toward it at full speed, but we cannot see what is coming. We're trapped in a tiny razor-thin slice of reality called the now. This is our prison. We are shackled to the present moment. This feeling, this flow of time, is the central experience of being alive. It is what gives life its urgency. It is what gives us the capacity for regret and the capacity for hope. But how does physics describe this river? Before Einstein came along, Isaac Newton gave us the definitions that we still use in our daily lives. Newton described time as absolute. He imagined that the universe had a master clock. Imagine a giant, invisible metronome ticking in the darkness behind the stars. Tick, tock, tick, tock. Newton believed that this tick was the heartbeat of God. It was the rhythm of reality, and most importantly, as he believed it, was universal. This means that a second is the same everywhere. If you boil an egg on Earth, it takes 3 minutes. If you boil an egg on Mars, it takes 3 minutes. If you boil an egg on a spaceship travelling at 1,000,000 miles per hour, it takes 3 minutes. We imagine that time is a flat sheet that covers the entire cosmos. Imagine taking a knife and slicing through the block of the universe. We call that slice right now. We intuitively believe that right now on Earth is the exact same moment as right now in the Andromeda Galaxy. We imagine that if you snapped your fingers, everything in the universe would freeze in that exact instant. The galaxy would freeze. The star would freeze. The coffee cup falling off the table would freeze. This is the concept of simultaneity. It comforts us. It makes us feel connected to the rest of the cosmos. It allows us to say things like, "I wonder what the aliens are doing right now." It assumes that there is a shared moment that we all inhabit together. And in this Newtonian view, time is completely separate from space. The river flows through the box, but it doesn't touch the box. The box doesn't get wet. The river doesn't change shape. They are two different tracks. This separation is what makes our lives manageable. We organize our entire civilization around this rigid grid of time. We set alarms. We make schedules. We count birthdays. We treat time as a resource. We spend it. We waste it. We save it. We treat it like a ruler that measures our duration. But there is a subtle problem with this intuition, a problem that philosophers noticed long before physicists did. If time is a river, how fast does it flow? Think about that. To measure a speed, you need to divide distance by time, miles per hour, meters per second. But if you want to measure the speed of time, what do you compare it to? Do you say, time moves at the rate of 1 second per second? That is meaningless. That is like saying a dollar is worth $1. It doesn't tell you anything. We feel the flow, but we cannot define the speed of the flow. Are we moving through time fast or slow? When you are bored, time seems to drag. When you're having fun, time seems to fly. Is that just a trick of the mind? Or is the river actually changing speed? In the Newtonian world, the answer was, it is a trick of the mind. Newton said the river is steady. It is the reference. It is the unshakable axis against which everything else is measured. It is the calm, mathematical tick, tick, tick that serves as the backdrop for all motion. So, this is the classical picture we are holding in our heads tonight. We have the empty box of space, rigid, infinite, 3D, and we have the flowing river of time, relentless, one way, universal. We are tiny boats floating down this river inside this box. We are separate from the river, we just ride it. And we are separate from the box. We just occupy it. It is a lonely picture in a way. It suggests that we are just passengers. The universe is a machine that runs on its own, and we're just fleeting ghosts passing through the gears. But it is a logical picture. It matches our common sense. It works for building bridges. It works for catching trains. It works for boiling eggs. But I want you to hold on to one specific thought as you drift off. Think about that master clock. Think about that invisible beat that keeps the whole universe synchronized. What if I told you it doesn't exist? What if I told you that the now you are experiencing is yours and yours alone? What if I told you that the river flows at a different speed for your head than it does for your feet? What if I told you that by simply standing up and walking across the room, you're decoupling yourself from the timeline of the person sitting on the couch? The intuition of the river is strong, but the river is a lie in the next chapter. We're going to break the clock. We're going to take this simple, comfortable picture of space and time, and we're going to introduce the glitch. We're going to introduce the thing that refuses to obey the rules of the box and the river. We're going to introduce light, and when we do, the walls of the box will melt and the river will start to loop. But for tonight, stay in the flow. Feel the heartbeat. Feel the second passing. Rest in the certainty of the ticking clock. It is the last time we will be able to trust it. We've been building a fortress. We built a world that makes sense. We built a world where space is a rigid, reliable box. We built a world where time is a steady, universal river. We built a world where here is always here and now is always now. This is the world of Isaac Newton. It is the world of common sense. It is the world that allows us to build skyscrapers that stand up straight and clocks that tell the truth. But tonight, we are going to find the crack in the foundation. We are going to introduce the one thing that refuses to obey the rules of the box and the river. We're going to introduce the glitch. That glitch is light. To understand why light is such a problem, we first have to understand how motion should work. We have to understand the logic of the playground. Imagine you are standing on a train platform at night. It is quiet. The air is cool. In the distance, you see a train coming. It is a fast train. It is moving at 100 miles per hour. On the roof of the train, there is a pitcher, a baseball player. He is holding a baseball. He winds up, and he throws the ball forward in the same direction the train is moving. He can throw at 100 miles per hour. Now, do the math. To the pitcher standing on the roof, the ball is moving away from him at 100 miles per hour. But to you standing on the platform, the ball is moving much faster. You add the speeds together. The speed of the train, 100, plus the speed of the throw, 100. You see the ball travelling at 200 miles per hour. This is called Galilean relativity. It is the intuitive math of the universe. Velocities add up. If you run forward and throw a spear, the spear goes faster. If you fire a cannon from a moving ship, the cannonball goes faster. This implies that there is no speed limit. If you get a faster train and a stronger pitcher, you can reach 300, 500, 1,000 miles per hour. You couldn't keep adding speed forever. This was the law of the land for 300 years. It was unbreakable. But in the late 1800s, physicists started playing this game with light beams instead of baseballs, and the game broke. Imagine the man on the train puts down the baseball. He picks up a flashlight. The train is still moving at 100 miles per hour. He turns on the flashlight. A beam of pure light shoots forward into the dark. We know from our measurements that light travels at a specific speed. Let's call it cm. It is roughly 670 million miles per hour. Now, let's do the math again. The man on the train sees the light moving away from him at speed. cm. You're on the platform. You get out your calculator. You expect to see the light moving at train speed plus light speed. 100. C. But you don't. When you measure the speed of that beam of light from the platform, you get c. Exactly c. Not a mile per hour faster, not an inch per second faster. The speed of the train disappeared. The light completely ignored the motion of its source. This is baffling. If I run toward you and throw a ball, the ball hits you harder. But if I run toward you and shine a light, the light hits you at the exact same speed as if I were standing still. It is as if the universe has a speed limit that is absolute. It doesn't matter how fast the source is moving. It doesn't matter how fast you are moving. The beam of light always travels at exactly 297,792,458 meters per second relative to whoever is looking at it. This sounds like a minor curiosity, a quirk of optics. But if you sit with it, really sit with it, you realize it destroys everything we built in chapters 2 and 3. Here is why. Think about what speed actually is. Speed is not a thing you can hold. Speed is a relationship. Speed is a ratio between space and time. Usually, we think space and time are the fixed things. We think a mile is a mile, and an hour is an hour. These are the constants, the box and the river, and because they are fixed. Speed is the variable. Speed can be anything we want, but the universe is telling us the exact opposite. The universe is saying, no, the speed of light is the fixed thing. The speed of light is the constant. And if the speed is locked, then distance and time must be the things that change. Think about the horror of that statement. If I am on the train and you are on the platform, and we both measure the same light beam moving at the same speed, even though I am chasing it and you are not, then our rulers must be different lengths, and our clocks must be ticking at different rates. To keep the speed of light constant, the universe literally warps the stage. If I speed up, the universe shrinks my space and slows down my time, just to ensure that the light beam stays ahead of me at exactly c. This is where the classical view dies. Newton's rigid box, it's gone. If I move fast enough, the box squashes, the walls contract. The distance is no longer absolute. A meter stick on a spaceship is shorter than a meter stick on Earth. Newton's steady river, it's gone. If I move fast enough, the river slows down. A second on the spaceship takes forever compared to a second on Earth. There is no master clock. There is no absolute grid. Suddenly, the universe feels much less stable. It feels like a house of mirrors. Everything is relative. My space is different from your space. My time is different from your time. The only thing we share, the only thing that is solid in this entire shifting, melting cosmos, is the light itself. This is the crisis of physics at the end of the 19th century. The experiments were screaming that light was constant, but our intuition was screaming that space and time were constant. They couldn't both be true. Something had to break. And for a long time, scientists tried to fix the light. They invented invisible substances, ethers and fluids, to try and explain why light acted so strangely. They tried to save the box in the river, but then a young patent clerk named Albert Einstein stepped in, and he said, "Stop trying to save the box, break the box." He realized that the only way to make sense of the universe was to accept that space and time are not separate things. They're not a stage and a clock. They are a single, flexible, dynamic material. They are space-time, and this material can stretch, it can squeeze, it can bend. It is the putty out of which reality is sculpted. This is the pivot point of our story. We have left the safe harbour of common sense. We're now drifting into the deep ocean of relativity. In the next chapter, we're going to meet Einstein properly. We're going to look at this new map he drew. We're going to stop seeing space and time as enemies and start seeing them as partners. We're going to learn how they trade with each other, how you can trade a bit of time to buy a bit of space. So, as you lie there tonight, try to feel the instability. The room you are in feels solid. The clock feels steady. But that is only because you are slow. If you were fast, the walls would close in, the clock would stop, and you would see the true, shivering fabric of the universe revealed. We stood on a train platform and watched the world break. We watched a beam of light disobey the laws of mathematics. We watched it travel at the same speed, no matter how fast we chased it. And because of that stubborn beam of light, we saw the walls of our absolute box crumble. We saw the flow of our absolute river stutter. We realized that if light is the constant, then space and time must be the variables. But what does that actually look like? It is one thing to say time changes. It is another thing to visualize it. How can a second be long for one person and short for another? Tonight, we're going to meet the man who drew the new map. We're not going to a grand university. We are not going to a futuristic lab filled with lasers. We're going to travel back to the year 1905, to a quiet, dusty room in Bern, Switzerland. It is a patent office. The air smells of ink and paper. The room is filled with the ticking of clocks and the scratching of pens. Sitting at a desk, hidden behind stacks of technical drawings for new motors and sorting machines, is a 26-year-old man. He is not yet the icon. He doesn't have the wild white hair or the famous sweater. He is young. He is neat. He is a third-class clerk. He is a nobody. But while his hands are busy stamping forms, his mind is drifting somewhere else entirely. Albert Einstein is dreaming about a mirror. He is playing a movie in his head. And tonight, I want you to play that same movie in yours. I want you to imagine a clock, but not a clock with gears and springs. Einstein didn't trust gears. Gears have friction. Gears get rusty. He wanted a clock made of the purest thing in the universe. He imagined a light clock. Imagine two perfect mirrors facing each other, one on the floor, one on the ceiling, between them. A single particle of light, a photon, bounces up and down. Tick, tock, tick, tock. It hits the floor. Tick. It hits the ceiling. Tock. Because the speed of light is perfectly constant. This is the most accurate clock in the universe. The time it takes for the photon to bounce up and down is 1 moment. Now, Imagine this clock is sitting on the floor of a train. The train is stopped at the station. You're sitting on the train, watching the clock. You see the photon going straight up and straight down, a perfect vertical line. Tick, tock, simple. But now, the train starts to move. It accelerates until it is moving incredibly fast. Let's say half the speed of light. You are still on the train. To you, nothing has changed. You are moving with the clock. You're sharing its motion. You look at the photon, and it is still going straight up and straight down. Tick, tock. Everything feels normal. But now, we shift the camera. Imagine you are standing on the platform outside, watching the train zoom past you. The walls of the train are transparent. You can see the clock inside. What do you see? The clock is moving sideways at millions of miles per hour. So, the photon cannot just go straight up and down anymore. If it did, it would hit the ceiling, but the bottom mirror would have moved out from under it. It would miss. So, to stay inside the clock, the photon has to travel diagonally. It moves up and right, then down and right. It traces a zigzag path through the air. Now, summon your geometry. Think about a triangle. The diagonal line, the hypotenuse, is always longer than the vertical line. This means that, from your perspective on the platform, the photon has to travel a longer distance to complete one tick. Now, remember the golden rule from Chapter 4, the rule that broke the universe. The speed of light is constant. The photon cannot speed up. It cannot hurry to cover that extra distance. It is locked at speed zn. So, we have a problem. We have a longer path, and we have the same speed. If you have to drive a longer distance, and you cannot drive any faster, what happens? It takes more time. This is the thunderclap. This is the moment reality splits. To the person on the train, the tick took 1 second. But to you on the platform, watching that diagonal path, the tick took longer. Maybe it took 1.5 seconds. You look at the moving clock and you see it ticking slowly. Tick, tock, and it's not just the clock. You look at the passenger on the train. You see him blink, and the blink happens in slow motion. You see him pour coffee, and the liquid oozes like honey. You see his heart beating, and it beats with a slow, lethargic rhythm. Einstein realized that motion is a thief. Motion steals time. If you move through space, you must pay for that motion by slowing down your movement through time. This is called time dilation, and it destroyed the idea of the universal river. There is no master clock. There is only my clock and your clock. And if we are moving at different speeds, they will never agree. But the rabbit hole goes deeper. Einstein realized that if time breaks, then now must break too. Let's go back to the train. Imagine there is a passenger in the middle of the car. He has a lamp. He turns it on. The light spreads out in a sphere. It hits the front wall of the car and the back wall of the car. To the passenger, the light hits both walls at the exact same instant. The distance is the same. The speed is the same. He says, these two events happen simultaneously. But you are on the platform. You're watching the train rush past. You see the light turn on. But as the light travels forward, the front wall of the car is running away from it. The light has to chase the wall. It takes little longer to catch it. And as the light travels backward, the back wall is rushing toward it. The wall crashes into the light. It hits sooner. To you. The events were not simultaneous. You saw the light hit the back wall first and the front wall second. Who is right? Is the passenger right? Or are you right? In the old physics, we would have thought about it. We would have asked, who is really moving? But Einstein said, you are both moving, or you're both standing still. It depends on your perspective. There is no God's eye view. There is no correct answer. For the passenger, the events were simultaneous. For you, they were sequential. This is the relativity of simultaneity. It means that the present moment is not a slice of bread that cuts through the whole universe. It is a personal bubble. My now applies only to me. Your now applies only to you. If we are standing next to each other, our bubbles overlap perfectly. But if one of us starts to move, our bubbles tear apart. We slide into different realities. This is a lonely thought, isn't it? It suggests that we are all trapped in our own private frames of reference. It suggests that the universe is fragmented. But Einstein didn't see it as fragmentation. He saw it as a new kind of unity. He realized that while space varies and time varies, there is something that stays conserved. He realized that space and time are just two sides of the same coin. Think about a currency exchange. You can trade dollars for euros. If you have more dollars, you have fewer euros. Einstein showed us that we can trade time for space. Right now, sitting in your chair, you're spending all your speed budget on time. You're travelling into the future at maximum velocity. But if you get up and run, you trade a tiny bit of that time motion to buy some space motion, because you spent some of your budget on space. You have less left for time, so you age a little bit slower. You're not just a body in a room. You're a navigator on a four-dimensional ocean. Every time you move, you're steering your ship. You're turning the wheel, tilting your path away from future and toward elsewhere. This is the beauty of Einstein's vision. He didn't break the world, he unified it. He showed us that space and time are not rigid, separate stages. They are a fluid, dynamic, interconnected medium. He gave us a new name for reality, not world, not cosmos, but space-time. And this space-time is not just a math concept. It is the fabric that you are woven into right now. It is the stuff that bends when you sleep. It is the stuff that stretches when you drive. So, as we finish this chapter, I want you to feel the trade-off. Feel yourself lying still. By being still in space, you are flying fast through time. You are riding the arrow of the future. But what happens when something really heavy sits on this fabric? What happens when a star, or a planet, or a black hole pushes down on this flexible mesh? That is where we are going next. We're going to find out that the shape of space-time is not flat. It has hills, it has valleys, and falling into those valleys is what we call gravity. But that is a story for next chapter. For now, rest in your personal frame of reference. Your clock is the only one that matters. We have arrived at a turning point in our journey. In the last few nights, we dismantled the world you thought you knew. We took the rigid box of space and we crushed it. We took the steady river of time and we slowed it down. We learned that if you move fast enough, your ruler shrinks and your watch stops ticking. It left us with a feeling of fragmentation. If my time is different from your time, and my space is different from your space, then is there any real world left? Or are we just drifting in separate subjective bubbles, unable to agree on what is true? Tonight, we are going to rebuild the world. We are going to find out that while the separate pieces of space and time are relative, their sum is absolute. We are going to discover that we are not living in a fragmented chaos. We are living in a single, solid, magnificent structure. We are living in space-time. To understand this structure, I want you to imagine a map. Picture a simple paper map of your hometown. On this map, there is your house and there is the grocery store. Let's say the store is 3 miles away. Now, imagine you lay this map on a table. You draw an arrow pointing north and an arrow pointing east. You can describe the location of the store using coordinates. You might say, the store is 2 miles north and 1 mile east. But now, imagine you rotate the map. You turn the paper 45 degrees. The north arrow points a different way now. If you measure the coordinates again, the numbers change. Now the store is, say, 1.5 miles north and 2.5 miles east. The north distance changed. The east distance changed. But, and this is the crucial part, the actual distance between your house and the store did not change. The line connecting them is still 3 miles long. You didn't move the building. You just changed your perspective. You just rotated the grid. Einstein realized that this is exactly what is happening when we move through the universe. But instead of north and east, our axes are space and time. When you start to move, when you get on a fast train or a rocket ship, you are not changing the universe. You're simply rotating your map. You're turning your perspective so that what used to be space is now a little bit of time, and what used to be time is now a little bit of space. This is why they are not separate things. They are ingredients in a mixture. Just like north and east are just different ways of talking about distance. Space and time are just different ways of talking about space-time. We usually think of the universe as 3 dimensions plus 1. 3 dimensions of room, length, width, height, and 1 dimension of flow, time. 3 plus 1. But physicists don't write it that way. They write it as 4. 4 dimensions, indivisible. I want you to try to visualize this new shape. It is difficult, because our brains are built for the African savanna, not for high-speed astrophysics. But we can feel it with metaphors. Imagine a loaf of bread. This loaf represents the entire history of the universe. One end of the loaf is the Big Bang. The other end is the end of time. Everything that has ever happened, and everything that will ever happen, is baked into this loaf. The dinosaurs are there, a slice of bread near the beginning. The pyramids are there, a slice of bread a little further down. You, reading this right now, are a tiny crumb in a slice near the middle, and the death of the sun is a slice near the end. In our everyday lives, we feel like we are a knife, slicing through the loaf 1 sheet at a time. We call the slice we're currently cutting now. We think the past is gone, the slices we already ate, and we think the future doesn't exist. The dough hasn't been baked yet. But relativity says, no, the whole loaf exists at once. If I am moving past you at high speed, my knife cuts the loaf at a different angle than yours. My now slice is tilted compared to your now slice. This means that my now might include parts of your future, and your now might include parts of my past. If we can disagree on what now is, then now cannot be the only thing that is real. For the math to work, the past must still be there, and the future must already be waiting. This leads us to the concept of the spiral, block universe. It suggests that space-time is a solid block of reality. It is a crystal of events. Think about what this means for you. Usually, we think of ourselves as transient things. We are born. We move around for a while, and then we vanish. We feel like fleeting sparks. But in the view of space-time, you are not a spark. You are a line. You are a long, winding worm embedded in the crystal. One end of your worm is your birth, the other end is your death. And the whole worm exists forever in the fabric of space-time. Physics calls this your world line. Your world line is woven together with the world lines of everyone you have ever met. When you hug someone, your two world lines tangle together for a moment in the block. When you sleep, your world line goes straight up the time axis. When you travel, your world line tilts sideways. This view takes away the anxiety of time. It says that yesterday is not lost. It is just over there. Just like New York is over there when you're in London. You can't see New York. You can't touch it. But you know it still exists. The past is simply a place on the map that you can no longer reach, because your train is moving forward. And speaking of moving forward, there is one more secret about this structure. We learned earlier that light travels at a specific speed limit, c. But there is a deeper truth. Everything in the universe travels at c-gang, even you, even right now. But you're not travelling at c through space. You're travelling at c through space-time. Imagine a car that has a gas pedal stuck to the floor. It is forced to go 100 miles per hour at all times. It can drive north, or east, or northeast. But the total speed on the speedometer must always be 100. You are that car. Your north is space. Your east is time. Right now, lying in your bed, you're not moving north through space. So, all of your speed, all 100 miles per hour of it, is directed east through time. You're hurtling through time at the speed of light. That is why you are aging. That is why tomorrow comes so fast. But if you get in a rocket ship and start moving through space, north, you have to steer the car. You divert some of that 100 mph speed away from time and put it into space, because your total speed is fixed. Your speed through time must drop. You age slower. If you could turn the wheel all the way to north, so that you're moving through space at the speed of light, you would have zero speed left for time. Time would stop. You would be frozen in the eternal now. This is the life of a photon. This explains why the speed of light is the limit. It isn't a barrier that prevents you from going faster. It is simply the total speed that every object possesses. You can spend it on distance, or you can spend it on duration, but you cannot create more of it. So, look at the room around you one last time tonight. It feels like an empty box, but it isn't. It is a thick, rich, four-dimensional gel. You are sliding through it right now. You're a geometric shape carving a path toward the future, and you are connected to everything else. The star billions of miles away is not far away in the old sense. It is just a different location on the same continuous sheet of fabric that touches your face. But this fabric is not just a passive stage. As we're about to find out, this fabric is flexible. It is elastic. What happens when you put something heavy on a trampoline? The fabric curves. It sinks. It pulls things toward it. In the next chapter, we're going to look at what happens when space-time stops being flat. We're going to learn the true definition of gravity. We're going to learn why the Earth orbits the Sun, not because it is being pulled, but because it is falling along the curves of the invisible map. But for now, be still. Let your world line go straight up toward tomorrow. Rest in the solid block of history. We've taken apart the universe, piece by piece. We remove the furniture, we remove the air, we remove the illusion of the rigid box, and we remove the illusion of the steady river. In their place, we built a new structure, a four-dimensional block called Spacetime. But I know that space-time can feel cold. It can feel like an abstract word that belongs on a chalkboard in a dusty university. When you close your eyes, you don't feel like you're living in space-time. You feel like you're living in a room. You feel like a person. You feel like a solid object sitting in a solid world. Tonight, we're going to change that. Tonight, we're going to stop looking at the map, and we are going to look at the territory. We're going to learn what this fabric is actually made of. It is not made of atoms. It is not made of energy. It is not made of stuff. Space-time is made of events. This is the shift we have to make to understand reality. We usually think of the universe as a collection of things, stars, planets, people, chairs, apples. We imagine these things moving around on the stage of space, changing as the clock of time ticks. But relativity asks us to stop seeing things. It asks us to start seeing points. Imagine snapping your fingers, sound of a snap. That snap happened at a very specific location. It happened at a specific latitude, a specific longitude, and a specific altitude. And it happened at a very specific split second of time. If you gave those four numbers to someone, the three space numbers and the one-time number, they could pinpoint that snap exactly in the history of the universe. That snap is an event. In physics, an event is the fundamental atom of reality. It is a single point in the four-dimensional block. It has zero size. It has zero duration. It is just a marker. Something happened here and now. Now, look at yourself. You think of yourself as a thing. You think of yourself as a 3D object that endures through time. But to the universe, you are not a thing. You are a swarm of events. Think about your life. Your birth was an event. Your first step was an event. Every breath you take is an event. Every time your heart beats, that is an event. If you string all these billions of tiny events together, like pearls on a necklace, you get a line, a continuous, winding path that stretches through the block of space-time. We call this your Sterney world line. If you could step outside of time and look at the universe, you wouldn't see people walking around. You would see these long, complicated strands woven into the fabric. You would see your world line twisting around the world line of your home. You would see it tangling with the world lines of your friends. You would see it running parallel to the world line of the Earth as it spirals around the sun. This is what space-time actually means. It is not a container for objects. It is a tapestry of histories. And this solves one of the oldest paradoxes of existence, the paradox of identity. Think about a photograph of yourself from 10 years ago. You look at that person. They have different hair. They have different cells. They have different thoughts. Are they you, or are they a stranger? In the old view of space and time, it is hard to say. The past is gone. That person doesn't exist anymore. You replaced them. But in the space-time view, the answer is simple. That person in the photo is just a different segment of the same world line. They are the tail of the worm, and you are the head. You are physically connected to them through the block of time. You are the same structure. But now, we have to ask a harder question. How do these events relate to each other? How do we measure the distance between them? In a normal room, measuring distance is easy. You take a tape measure from the wall to the table, 5 feet, done. But in space-time, the walls are moving, and the clocks are changing speed. If I am moving fast, I might measure the distance between two events as being very short because my space shrank. But you, standing still, might measure the distance as very long. If we can't agree on distance and we can't agree on time, is there anything we can agree on? Yes, there is a secret ruler, a ruler that works in 4 dimensions. It is called the Spacetime interval. This is the magic of Einstein's geometry. He found that while space changes and time changes, the combination of them stays constant. Think of it like a seesaw. If space goes up, time goes down. If space goes down, time goes up. But the interval, the balance point, never changes. This interval is the true distance of the universe. It tells us how far apart two events really are, stripped of our human perspective. And this brings us to the most beautiful and terrifying shape in physics, the shape that defines your destiny. The light cone. I want you to visualize a single event. Let's say you, right now, lying in bed. That is the center point. Now, imagine a flash of light exploding from your chest, traveling outward in all directions. Because light travels at a fixed speed, that flash creates a growing sphere of light. 1 second later, the sphere is 186,000 miles wide. 1 year later, the sphere is 1 light year wide. If you draw this expanding sphere on a graph, with time going up, it forms a cone, an upside-down ice cream cone, growing wider as it goes higher into the future. This is your future light cone, and here is the rule. You can only affect things inside this cone, because nothing can travel faster than light. You can never send a message, or travel, or touch anything outside of this cone. The cone marks the boundary of your influence. Anything inside the cone is your future. You can go there, you can change it. Anything outside the cone is the elsewhere. The elsewhere is a strange ghost land. It consists of parts of the universe that exist right now, but are completely untouchable to you. You cannot see them, they cannot see you. You are causally disconnected, and there is another cone below you. The past light cone. This represents all the light rays that have ever reached you. Everything that has ever happened in your past that could have affected you lies inside this bottom cone. So, here you are, a tiny event, pinched between 2 infinite cones. The past pushes up from below, the future opens up above, and the walls of the cone are the speed of light. They are the rigid slopes that you cannot climb over. This geometry explains why we feel trapped in the now. We are sliding up the inside of the cone. We are surfing the wave of causality. It also explains why space-time is not just a jumbled mess, even though time can stretch and shrink. The order of causes is protected by the cones. You can never kill your grandfather before you were born, because that would require jumping out of your light cone. It would require moving faster than light. The cones keep the story straight. They ensure that the coffee cup breaks after. It falls, never before. They ensure that the message arrives after it is sent. So, when you look at the night sky tonight, don't just see stars, see the cones. Every star is the center of its own light cone. Every person is the center of their own light cone. We are a forest of cones, growing upward through the block of space-time. When our cones overlap, we can talk to each other. We can touch. We can love. When our cones are separate, we are alone. Space-time is the map of these connections. It is the ledger of who can talk to whom. And this structure, this fabric of events and cones, is what we are moving through. But so far, we have treated the fabric as if it were flat. We have assumed the cones are perfect, straight, rigid shapes. But the universe is not empty. The universe is filled with heavy things. Earth, the sun, black holes, and these heavy things do something incredible to the cones. They tip them over. They grab the fabric of space-time and they pull. In the next chapter, we're going to start moving. We're going to learn what it means to travel through this warped landscape. We're going to learn why, even when you think you are sitting still, you are actually rushing along a curve. We're going to open the door to gravity, but for tonight, simply exist as an event. You are a point in the dark. You are a coordinate. You are here. X. Z. You are now. T. And your world line is waiting for tomorrow. We have spent the last chapters building a sculpture. We took the chaos of the universe and we froze it into a block. We learned that reality is a four-dimensional crystal called space-time. We learned that you're not just a person, you're a geometric line, a world line woven into this crystal. But so far, our view has been static. We have been looking at the block of space-time like a museum exhibit. We have been looking at the future and past as places on a map. Tonight, we need to breathe life into this map. We need to talk about motion. I want you to lie very still. Relax your muscles. Let your breathing slow down. Feel the heaviness of your blankets. Listen to the silence of the room. To your senses. You are perfectly stationary. You're not going anywhere. The bed is not moving. The room is not moving. You feel anchored. But I am here to tell you that your senses are deceiving you. In the eyes of physics, you are currently traveling at a terrifying speed. You're hurtling through the universe at the ultimate velocity. You're moving at the speed of light, right now, even while you sleep. This sounds impossible. We know that massive objects like human beings cannot move at the speed of light. We learned that in earlier chapters. If you tried to move through space at light speed, your mass would become infinite and the universe would break. So, how can I say you are moving at light speed? Because you are not moving through space. You're moving through space-time. This is the great secret of relativity. The speed of light, that famous number, c-sist, is not just the speed limit for light. It is the speed of everything. Every atom in your body, every star in the sky, every dust mote floating in the air is moving through the four-dimensional environment at exactly 299,792,458 meters per second. You cannot go faster. And here is the twist. You cannot go slower. Your speed through space-time is fixed. It is locked. It is absolute. So, if we are all moving at the same speed, why does it feel like we can stop? Why does it feel like a race car is faster than a parked car? It comes down to direction. I want you to visualize the car on the salt flat again, but tonight we're going to drive it. Imagine a vast, perfectly flat white desert. It stretches out in all directions to the horizon. You are in a sleek silver car. This car has a peculiar feature. The gas pedal is welded to the floor. The engine is locked at maximum RPM. The speedometer is stuck at light speed. You have no brakes. You have no accelerator. You're always moving at sack. But you have a steering wheel. And on this salt flat, the directions are not north and west. The directions are space and time. Let's say that north represents space and east represents time. Right now, lying in your bed, you're steering your car directly east. You're not moving through space north. Your spatial speedometer reads 0, but because your total speed is locked at sig, All of that speed must be directed east. You are barreling through time at maximum velocity. We experience this velocity as aging. We experience it as the relentless flow of seconds turning into minutes. The reason time feels so unstoppable, the reason it feels like a roaring river dragging you forward, is because you are hitting it at full speed. You're colliding with the future at 670 million miles per hour. This is the default state of matter. To be still in space is to be fast in time. But now, imagine you want to move. You get up to walk to the kitchen. In our car metaphor, this means you turn the steering wheel slightly to the left. You want to make some progress toward the north, space. But you only have a fixed amount of speed to spend. The total length of your arrow cannot change. So, if you turn the car to point slightly north, it must point slightly less east. You are borrowing speed. You are diverting some of your velocity away from time and pouring it into space. This is the trade-off. This is the currency exchange of the universe. To move through space, you must slow down your movement through time. And this is not just a metaphor. This is literal. When you walk to the kitchen, your watch actually ticks slower than the watch left on the nightstand. Your heart beats slower. Your cells age slower. You're not moving through time as fast as the room you left behind. Now, in our daily lives, this effect is tiny. Human walking speed is pathetic compared to the speed of light. It's like turning the steering wheel by a fraction of a degree. You're still going 99.9999999% east. The difference is billionths of a nanosecond. Too small to notice. But what if you had a real rocket? What if you could turn the wheel hard? Imagine you turn the car 45 degrees. Now you're moving through space at half the speed of light. And you're moving through time at, well, the math is a bit triangular, Pythagoras, but roughly 86% of your normal speed. You are aging significantly slower than the people back on Earth. They are racing east. You're drifting northeast. When you eventually turn back and meet them, they will be further down the timeline than you. They will be older. And now, let's take it to the limit. Imagine you turn the steering wheel all the way to the north. You point your car directly into space. You pour every single drop of your velocity into spatial motion. You're now moving through space at c-g. What is your speed through time? 0. You have no speed left for the eastward journey. You've stopped aging. You have stopped experiencing duration. The now freezes forever. This is the life of a photon. Light moves through space at the maximum possible speed. Therefore, light does not move through time at all. From the perspective of a photon, the moment. It is created in a star, and the moment it hits your eye 1,000,000 years later are the same moment. To a photon, there is no waiting, there is no distance. The emission and the absorption happen instantly. The universe is collapsed into a single point of here and now. It is only us, the heavy, slow creatures made of mass, who experience time. We experience time because we are broken light. We are energy that has been trapped, slowed down, and forced to drift sideways through the temporal dimension. So, I want you to reconsider the feeling of weight you have right now. You feel heavy on the mattress. That heaviness is actually a symptom of your motion. Because you are massive, you are stuck travelling mostly through time. You're locked on the eastward heading. You're a time traveller. That is your primary job. Your job is to carry the past into the future. When we look at the universe this way, Motion becomes geometry problem. It is all about angles. When a planet orbits a star, it is following a spiral path through this 4D landscape. When an electron spins around an atom, it is dancing through the time stream. And this explains why the laws of physics look the same for everyone. Remember the train paradox. Why did the person on the train think their time was normal? Because inside their car, they are still facing east. To them, they are the ones sitting still. They are the ones with the gas pedal floored in the time direction. It is only when you look at them that you see their arrow is tilted. You see them moving through space, so you deduce that they must be moving slower through time. It is a perspective trick, like two ships sailing on the ocean. If I sail north and you sail northeast, I look at you and say, you are falling behind. You aren't making as much progress north as I am. And you look at me and say, no, you are the one going the wrong way. We're both moving at the same speed. We are just disagreeing on the direction. So, tonight, as you drift towards sleep, think about your world line. Think about that long invisible thread that represents your life. Right now, as you lie still, your thread is shooting straight up. It is growing tall. It is climbing the ladder of time second by second. Tomorrow morning, when you get up, your thread will start to wiggle. It will bend left and right as you walk. It will tilt as you drive to work. You will make tiny, microscopic adjustments to your rate of aging. You're a sculptor of space-time. With every step you take, you are carving a unique path through the crystal. And even though we're all travelling at the speed of light, we're doing it together. We are a fleet of cars, driving mostly parallel, keeping pace with each other on the road to tomorrow. The fact that we stay together, the fact that I don't age 10 years while you age 5 minutes, is a miracle of our shared velocity. It is because we're all trapped in the slow lane of space, which is the fast lane of time. But what happens when the road isn't flat? We've been driving on a salt flat, smooth, level, predictable. But the universe is not flat. The universe has bumps. It has potholes. It has deep, terrifying canyons. Massive objects, like the Earth and the Sun, bend the road. And when the road bends, the car turns, whether you touch the steering wheel or not. In the next chapter, we're going to look at what happens when your car hits a curve. We're going to find out that falling is just following the road. We're going to discover the true nature of gravity. But for now, keep your hands on the wheel. Keep your eyes on the horizon. You're a traveller of light speed. In the last chapter, we sat in the driver's seat of a car that never stops. We learned that you are always moving through the 4-dimensional landscape of space-time at the speed of light. We learned that motion is just a matter of steering. You can steer toward space, or you can steer toward time. But tonight, we need to look at the consequences of that steering. It is one thing to say, if you move fast, time slows down. It is a neat little sentence. It fits on a t-shirt. But what does it actually mean? Does it mean the clock breaks? Does it mean your brain works slower? Does it mean you live longer? Tonight, we are going to explore the most famous and perhaps the most melancholy story in all of physics. It is a story about two people. Let's call them Alice and Bob. And it is a story about how speed can tear them apart, not just in distance, but in history. We call this story the twin paradox. I want you to imagine two identical twins. They are 20 years old. Alice is an astronomer. She loves the quiet of the observatory. She decides to stay on Earth. Bob is an astronaut. He loves the speed of the void. He signs up for the first mission to a distant star. The star is Wolf 1061. It is exactly 14 light years away. Bob's ship is a miracle of engineering. It can travel at 99% of the speed of light. The day of the launch comes. They hug goodbye. Alice stands on the platform and watches the ship rise on a pillar of fire. She knows she's going to wait for him. She does the math in her head. This star is 14 light years away. He's going at nearly light speed. It will take him about 14 years to get there and 14 years to come back. She sighs. She knows she will be 48 years old when she sees her brother again. Bob leaves the atmosphere. He pushes the throttle. He steers his Spacetime car sharply toward the north. He diverts almost all of his velocity into space. He leaves only a tiny sliver of speed for time. Now, let's sit with Bob on the ship. What does he feel? Does he feel like he is in slow motion? Does he talk like a record being played at low speed? Hello, Alice. No. Inside the ship, everything is perfectly normal. Bob breathes at a normal rate. His heart beats 70 times a minute. He boils a cup of tea and it takes 3 minutes. He reads a book. He sleeps. The laws of physics inside his ship are untouched. Remember the principle of relativity. If you are moving smoothly, you are at rest. But Bob looks out the window, and he sees something impossible. He knows the star is 14 light years away. He knows his ship cannot go faster than light, so he expects the trip to take 14 years. But he looks at his flight computer. The computer says, time to destination, 2 years. Bob is confused. How can I cross 14 light years in 2 years? That would mean I am travelling 7 times faster than light. That breaks the rules. But then, Bob looks at the universe outside. The stars look different. The distance between Earth and Wolf 1061 doesn't look like 14 light years anymore. Space itself has been squashed. Because Bob is moving so fast, the universe is flattened in front of him like a pancake. The vast distance has shrunk to a mere 2 light years. This is length contraction. Bob isn't moving faster than light. He's simply taking a shortcut that he created by moving fast. The universe shortened the road to accommodate his speed. So, Bob flies for 2 years. He reaches the star. He takes some pictures. He turns around. He flies back. Another 2 years. To Bob, the entire mission took 4 years. He is now 24 years old. Ideally, he has a bit of stubble. He feels great. He's ready to tell Alice about his trip. He lands on Earth. He opens the hatch. The steam clears. He walks down the ramp, expecting to see his sister, who should be 48. But Alice is not 48. Alice is an old woman. Or maybe she is gone, because while Bob experienced 4 years, the Earth experienced 28 years. Actually, at 99% light speed, the math is even more extreme. The time dilation factor is about 7 to 1. So while Bob aged 4 years, Alice aged 28 years. She is 48. Okay, my mental math was close. But imagine if he went faster. Imagine he went at 90% plus 999% light speed. He could go to the galaxy Andromeda. The trip might take him 50 years. He would come back an old man. But on Earth, 5 million years would have passed. The human race would be extinct. The continents would have drifted. The sun would be hotter. He would be a ghost returning to a world that has forgotten him. This is the tragedy of time dilation. It means that time is not a shared environment. It is a personal resource, and you spend it depending on your speed. Alice spent her time waiting. She took the long path through time. Bob spent his time moving. He took the short path through time. In the diagram of space-time, A straight line is actually the longest distance between 2 points in time. By zipping around at high speed, Bob effectively skipped over the timeline of Earth. He travelled into the future, and this is the crucial realization. We are all time travellers. We're all travelling into the future, every second of every day. But speed allows you to change the rate of that travel. Speed is the throttle on your time machine. But notice something important. The throttle only goes one way. You can slow down your clock, which makes you arrive in the future faster. But you can never, ever turn the clock backward. You can never go back to Alice when she was young. The path is closed. The geometry prevents U-turns. So, is this just a story? Is this just a mathematical fantasy? No, it is happening to you right now. Open your phone. Look at the blue dot on the map. That dot knows where you are because of a network of satellites orbiting the Earth. The GPS satellites. These satellites are moving at 17,000 miles per hour. That is fast. According to Einstein, their clock should be ticking slower than the clocks on the ground. There's also a gravity effect which makes them tick faster, but the motion effect fights it. The engineers who built the GPS system had to program the satellites to compensate for this drift. They literally had to program the clocks to tick wrong so that they would match the Earth. If they didn't believe in Einstein, if they ignored time dilation, the GPS system would drift by about 10 kilometers every single day. Within a week, your phone would tell you that you're in the middle of the ocean. The entire modern world relies on the fact that time is flexible. We also see it in subatomic particles. There are tiny particles called moons. They are created in the upper atmosphere when cosmic rays hit the air. Moons are unstable. They die very quickly. They live for only 2 microseconds, even travelling at the speed of light. 2 microseconds is not enough time to reach the ground. They should all die high up in the sky. We should never see a muon down here, but we do. We detect them in our labs all the time. Why? Because the muons are falling at 99.9% of the speed of light. For them, time slows down. Their 2 microseconds get stretched out. They live long enough to reach the surface, or, if you ask the muon, the distance to the ground shrank. Either way, they survived because of relativity. So, tonight, think about the loneliness of speed. We dream of going fast. We dream of warp drives and hyperjumps. We want to see the universe. But the universe charges a tax. The tax is connection. If you want to stay connected to the people you love, you have to stay synchronized with them. You have to move at the same speed. You have to share the same now. This is why we're all huddled together on this slow, heavy rock. Being slow is what keeps us together. Being slow is what allows us to have a shared history. If you were to leave, if you were to accelerate, you would be peeling your world line away from the braid of humanity. You would be stepping into a lonely future. So, be grateful for the heaviness of your blankets. Be grateful for the gravity that holds you still. It is anchoring you to the timeline of your family, your friends, and your life. You're moving through time together, and that is a beautiful thing. But we have one more mystery to solve. We have talked about speed curving time, but we haven't talked about the other thing that curves time. We haven't talked about the monster under the bed. We haven't talked about the force that grabs the fabric of space-time and twists it into a knot. In the next chapter, we are going to look at gravity. We are going to find out that falling isn't about being pulled. It's about sliding. And we're going to learn why your feet are actually slightly younger than your head. We have journeyed through the strange, high-speed world of special relativity. We learned that the speed of light is the cosmic limit. We learned that time is flexible, stretching and shrinking depending on how fast you move. We learned that you are a traveller in a four-dimensional block called Spacetime, but there has been a ghost in our machine, a missing piece. In all our examples so far, we have talked about coasting. We talked about trains moving smoothly. We talked about spaceships drifting in the void. We talked about a universe that is flat, smooth, and empty. But the real universe is not empty. It is filled with heavy things, stars, planets, black holes, galaxies, and it is filled with the mysterious force that holds them all together. Tonight, we must talk about gravity. I want you to feel the bed underneath you right now. Feel the pressure on your back. Feel the weight of your head on the pillow. If you were to roll off the edge of the bed, you know exactly what would happen. You would fall. You would accelerate downward until you hit the floor. Why? For 300 years, we thought we knew the answer. We thought the answer was the force. Isaac Newton, the father of classical physics, described gravity as an invisible tether. He imagined that the earth was reaching out with ghostly hands, grabbing your body and pulling it down. He imagined that the sun had a giant invisible rope attached to the earth, swinging it around in a circle like a cowboy spinning a lasso. To Newton, gravity was a thing. It was an active agent. It was a force that reached across the vacuum of space to grab objects and yank them closer. This view works perfectly for building bridges and firing cannons. But it bothered Newton. He didn't like the idea of action at a distance. How does the Earth know the sun is there? How does the rope work across 93 million miles of nothingness? He never found the answer, but in 1907, Albert Einstein found it. He was sitting in his chair at the patent office, staring out the window, and he had what he later called the happiest thought of my life. I want you to imagine this thought with me. Imagine a man falling off the roof of a house. Don't worry, he lands safely in a pile of hay. But for the few seconds that he is falling, what does he feel? Does he feel heavy? No, he feels weightless. If he drops his keys while he is falling, they don't fall to his feet. They float right next to his face. If he spills a cup of water, the water hovers in the air as a globule. Einstein realized something profound. Falling is indistinguishable from floating. If you woke up inside a sealed elevator and you were floating in the air, you wouldn't know if you were in deep space or if you were falling down a shaft on Earth. The physics is exactly the same. This led Einstein to a terrifying conclusion. If falling feels like doing nothing, then falling is doing nothing. Falling is the natural state of motion in the universe. So, why do you feel heavy right now? You're not falling. You are lying still. You feel heavy because the bed is pushing you up. Gravity is not a force that pulls you down. Gravity is the fact that the floor is interrupting your natural fall. The earth is constantly rushing up to meet you, preventing you from following your natural path through the universe. But if falling is natural, why do we fall down? Why doesn't the man fall up or sideways? Why do all paths lead to the center of the earth? This is where the geometry comes in. This is where space-time stops being a box and starts being a valley. Einstein realized that mass does not pull on distant objects. Mass distorts the fabric of reality itself. I want you to visualize a mattress, a pristine, flat, soft mattress. Now, place a heavy bowling ball in the center. What happens? The mattress sinks, it curves, it creates a deep depression, a dimple in the fabric. Now, take a marble, place it on the edge of the mattress and give it a gentle flick. Does the marble travel in a straight line? No. It follows the curve. It rolls around the bowling ball. It circles it. Eventually, it spirals inward and hits the ball. Now, look closely at the marble. Does the bowling ball reach out and grab the marble? No. Does the bowling ball have an invisible rope? No. The bowling ball isn't doing anything to the marble at all. The bowling ball has changed the mattress, and the marble is simply trying to move in a straight line through a curved environment. This is general relativity. Matter tells spacetime how to curve, and spacetime tells matter how to move. When you see the Earth orbiting the Sun, it is not being swung by a rope. The Earth is trying to fly in a straight line. It is trying to mind its own business. But the Sun is so heavy. It has created a massive valley in the fabric of space-time. The Earth is rolling along the walls of this valley. It is caught in the bowl, and this explains why everything falls at the same speed. If you drop a hammer and a feather on the moon, where there is no air, they hit the ground at the exact same instant. In Newton's world, this is a weird coincidence. Why would the heavy hammer and the light feather be pulled with the exact right force to match their speeds? But in Einstein's world, it is obvious. They are falling at the same speed because they are sliding down the same slope. The slope is the shape of space. It doesn't care what is sliding down it. So, gravity is not a force. Gravity is curvature. But here is the part that is hard to visualize. When we look at the bowling ball on the mattress, we are seeing 2D space curving into a 3D hole. But the real universe is 4D. It is space-time that is curving. And for things that are moving slowly, like us, it is actually the time part that curves the most. This is the strangest secret of gravity. Gravity makes time run slower. Imagine the bowling ball again. The closer you get to the heavy object, the deeper you are in the well, and the deeper you are in the well, the slower time flows. This is called gravitational time dilation. Right now, your feet are closer to the center of the Earth than your head. Therefore, your feet are deeper in the gravity well. Therefore, time is moving slower for your feet than for your head. Your feet are aging slower than your brain. The difference is tiny, billionths of a nanosecond over a lifetime. But it is real. If you live in a basement apartment, you age slightly slower than someone in a penthouse. If you live on Earth, you age slower than an astronaut in deep space. This is the true mechanism of falling. Your body wants to go where time is slowest. In the geometry of space-time, objects naturally curve toward the slow time regions. You fall down because the future down there is slower than the future up here. The Earth is literally a time sink, dragging you into a slower existence. This radical idea changed everything. It meant that space is not a passive stage. It is an active player. It can ripple. It can bend. It can twist. If two black holes crash into each other, they don't just create an explosion of matter. They create an explosion of space. They send ripples of geometry outward at the speed of light. These are gravitational waves. They stretch and squeeze the Earth as they pass through. Your body gets slightly taller and slightly thinner for a split second when a wave passes. We detected these for the first time in 2015. We heard the universe ringing like a bell. So, tonight, as you lie there, rethink your sensation of weight. Do not feel it as a pull. Feel it as a slide. You're on a slope, a 4-dimensional hill created by the massive rock beneath your house. Your body wants to slide down that hill toward the center of the earth. But the mattress, the bed, is getting in your way. You're caught in a standoff between the curvature of the universe and the electromagnetic strength of the atoms in your bed springs. The universe says, fall. The bed says, stop. And the result is the feeling of weight. This theory, general relativity, is the most beautiful theory ever discovered. It explains the orbit of Mercury. It explains the bending of light around stars. It predicted black holes before we even knew they existed. But it is also a theory of connection. It tells us that we are not separate from the space around us. We are dimpling it. You, yes, you, have mass. Therefore, you are bending space-time. It is a tiny, imperceptible bend. But it is there. You're pulling on the earth just as much as the earth is pulling on you. You're creating a tiny valley that the dust motes in the room are rolling into. You are a geometric feature of the universe. So, we have solved the mystery of the force. There is no force, there is only the shape. But visualizing 4D curvature is hard. Our brains hurt when we try to imagine time curving into space. In the next chapter, we're going to try to see it. We're going to use some gentle mental images to visualize how a straight line can become a circle without any force acting on it. We're going to learn how to see the invisible hills, but for now, rest in the valley. Let the curvature hold you. You are exactly where the geometry of the universe wants you to be. In the last chapter, we dropped a heavy truth on you. We told you that gravity is not a force. We told you that the earth is not pulling you down. We told you that you are sliding down a 4-dimensional slope created by the curvature of space-time. It is a beautiful sentence. Matter tells space-time how to curve. But I know that for many of you, it is just a sentence. It is hard to close your eyes and see it. Our human brains are built for a flat world. We understand flat tables. We understand straight roads. We understand that parallel lines never meet. When physicists talk about curved 4D spacetime, our minds tend to bounce off the idea. It feels like a headache waiting to happen. So tonight, we are going to heal the headache. We are not going to use equations. We are not going to use jargon. We're going to use simple, gentle mental images. We are going to learn how to visualize the invisible geometry that holds your feet to the floor. I want you to start by imagining a world that is simpler than ours. Imagine a world that is purely 2-dimensional. Imagine a vast, infinite sheet of white paper. Now, imagine 2 tiny explorers. Let's call them the beetles. These beetles are flat creatures. They live in the paper. They cannot look up or down. They only know forward, backward, left, and right. To them, their universe feels perfectly flat. It feels like an infinite plane. Now, suppose these 2 beetles stand on the equator of a giant sphere. They don't know it's a sphere, they think it's a flat world. They stand 1,000 miles apart. They both face strictly north. They check their compasses. They check their protractors. They make absolutely sure that their paths are perfectly parallel. They begin to walk. According to the rules of flat geometry, parallel lines never meet. If they walk straight north and never turn left or right, they should remain 1,000 miles apart forever, but they are walking on a sphere. As they march upward toward the North Pole, the surface of their world is subtly curving underneath them. They don't feel it. They don't feel any force pushing them sideways. They're putting one foot in front of the other, following a straight line. But slowly, mysteriously, the distance between them begins to shrink. After a few weeks, they're only 500 miles apart. After a month, they're only 100 miles apart. The beetles are confused. "I didn't steer right," says one. "I didn't steer left," says the other. "Something must be pulling us together." Eventually, at the North Pole, they crash into each other. If these beetles are stubborn, they will invent a force to explain this crash. They will say, "There is a mysterious magnetic attraction between our bodies that pulled us together." They will write laws about this force. They will give it a name. Maybe they will call it gravity. But we, looking down from the third dimension, know the truth. There was no force. There was no attraction. There was only geometry. The shape of their universe forced their straight paths to converge. They were following geodesics, the straightest possible lines on a curved surface. This is exactly what is happening to us. We are the beetles. We look at an apple falling to the ground and we say, "A force pulled it down." But in reality, the apple and the earth were just moving along their natural straight path through space-time. And those paths happen to crash into each other because the universe is curved. But this analogy has a flaw. The beetles move through space. But you, sitting in your chair, are falling toward the floor even though you aren't moving through space. How can you curve if you are standing still? This brings us to the second visualization, the visualization of time curvature. This is the most important mental image you will ever learn for understanding gravity. Remember the car from Chapter 8? The car that is always driving at the speed of light? You're in that car right now. You're driving east toward the future at maximum velocity. Now, imagine you're driving this car on a highway. But this highway has a strange surface. The pavement is not uniform. On the left side of the lane, the pavement is smooth and hard, clean asphalt. On the right side of the lane, the pavement is sticky. It is thick, deep mud. What happens if you try to drive straight down this road? Your left wheels move fast on the asphalt. Your right wheels get bogged down in the mud. They turn slower. If the left side is fast and the right side is slow, the car will naturally pivot. It will turn to the right. You don't have to touch the steering wheel. The difference in speed causes the turn. The car effectively falls into the mud. This is exactly how gravity works. The mud is the slowing of time. Recall from Chapter 10 that massive objects like the Earth slow down time nearby. Time runs slower near the floor than it does near the ceiling. Now, look at your body. You are the car. Your head is further away from the earth. It is in the fast time zone, the asphalt. Your feet are closer to the earth. They are in the slow time zone, the mud. Because your feet are moving through time slightly slower than your head, your entire world line pivots. Your path through the universe curves downward. You're not being pulled by the earth. You're simply swerving toward the slower time. Your future is tilting toward the ground because the ground is where the brakes are. This is why falling happens. Falling is just your body trying to veer into the slow lane of history. Now, I want you to try to visualize this in the room with you. Open your eyes for a moment, or just visualize the room in your mind. See the empty space between you and the wall. Usually we see it as empty air, but I want you to see it as a thick, clear jelly. Imagine that this jelly is denser near the floor and thinner near the ceiling. This density represents the flow of time. Thick jelly, slow time, thin jelly, fast time. If you throw a ball across the room, it has to fly through this jelly. The bottom of the ball drags in the thick, slow time. The top of the ball flies in the thin, fast time. So the ball curves downward. It arcs toward the floor. It isn't being pulled. It is just negotiating the texture of reality. This mental image works for everything. It explains orbits. Imagine the sun. The sun is a massive object. It creates a deep, deep puddle of slow time around it. The Earth is flying past the sun. The side of the Earth facing the sun is in slower time than the side facing away. So the Earth is constantly pivoting toward the sun. It wants to fly straight, but the mud of the sun's gravity keeps turning its steering wheel, so it goes in a circle. For billions of years, the Earth has been falling around the curve, forever turning toward the slow time, but never quite hitting the center. It is a dance of perfect balance. The momentum of the Earth wants to carry it out into the dark. The curvature of space-time wants to pivot it into the light. And the result is the stable, beautiful orbit that gives us our year. So, we have replaced the invisible ropes with something much more elegant. We have replaced force with terrain. Gravity is the landscape. Space-time has hills, stars, and valleys, black holes. It has smooth plains, deep space, and choppy waves, gravitational radiation. And you are a traveller on this terrain. Every time you stand up, you are fighting the geometry. You are pushing your body away from the slow time. Every time you lie down, you're surrendering to the curve. This view makes the universe feel less mechanical and more organic. It feels like a fabric that responds to presence. When you walk into a room, you bring your own little dimple of gravity with you. You change the shape of the room just by being in it. But if the Earth can curve space a little bit, and the sun can curve it a lot, what happens if we put too much mass in one place? What happens if we make the mud so sticky, so deep, that time doesn't just slow down, but stops? What happens if the curve becomes a cliff? In the next chapter, we are going to travel to the most extreme places in the universe. We're going to visit the monsters. We're going to look at the objects that break the fabric. We're going to talk about black holes. But for tonight, stay here on the gentle slope of Earth. Feel the subtle turn of your world line. Visualizing the curve is hard work. You have earned your rest. Let the geometry hold you. We learn to see the invisible. We learn that the empty air around us is not empty at all. It is a thick, jelly-like fabric called space-time. We learned that gravity is not a force that pulls you down, but a curvature in that fabric that you slide into. But so far, we have stayed in the shallow end of the pool. We have talked about the Earth. The Earth is heavy to us, but to the universe, it is nothing. It is a speck of dust. The dent it makes in space-time is tiny. It is a gentle, grassy slope. Tonight, we're going to leave the shallow end. We're going to swim out into the deep ocean of the cosmos. We're going to visit the heavyweights, the stars, the neutron stars, the monsters. We're going to see what happens when the fabric of reality is pushed to its breaking point. We're going to look at the geometry of the sack hole. I want you to imagine space-time as a vast, stretched rubber sheet. This is a classic analogy, but tonight we are going to push it further. Imagine deep space, far away from any galaxy. The sheet is perfectly flat. If you roll a marble across it, it travels in a perfectly straight line forever. This is the flat space-time of special relativity. It is calm. It is simple. Now, let's drop a star onto the sheet. Let's drop our sun. The sun is huge. It weighs 333,000 times as much as the Earth. When it lands on the sheet, it sinks. It creates a deep, a wide funnel. The sheet stretches downward, creating a gravity well that extends for billions of miles. The planets, Mercury, Venus, Earth, Mars, are like marbles rolling around the inside of this funnel. They are moving fast enough to keep from falling into the hole, but the curve keeps them trapped in a circle. But even here, near the sun, the curve is smooth. You could fly a spaceship close to the sun, and if your engines were strong enough, you could climb back out of the funnel. The slope is steep, but it is climbable. Now, let's turn up the gravity. Imagine a star that is much, much heavier than the sun, and imagine it dies. It runs out of fuel. It collapses under its own weight. It crushes itself down into a ball only 10 miles wide. This is a neutron star. A teaspoon of this star weighs as much as Mount Everest. If you dropped this ball onto our rubber sheet, it wouldn't just make a funnel, it would make a spike. The fabric would be pinched downward violently. If you stood on the surface of a neutron star, the gravity would be 200 billion times stronger than on Earth. The time dilation we talked about earlier, it is no longer a tiny fraction of a second. If you spent a few years on a neutron star, decades would pass back on Earth. The slope is becoming slippery. The mud of slow time is becoming quicksand. But nature doesn't stop there. What happens if you pile too much mass onto the sheet? What happens if the object is so heavy and so small that the fabric cannot support it? The fabric rips, or, more accurately, it plunges downward infinitely. It creates a bottomless pit, a puncture, as a black hole. Tonight, I want to give you a new way to visualize a black hole. Don't think of it as a solid object. It isn't a planet. It isn't a star. It isn't a thing. It is a place where space-time itself is flowing like a waterfall. Imagine a river flowing toward a cliff. As the water gets closer to the edge, it speeds up. At first, the current is slow. You can swim against it. Then it gets faster. You have to swim harder to stay in place. Then it reaches the edge. The water pours over the cliff at a terrifying speed. Einstein's equations suggest that near a black hole, space itself is falling into the hole. Space is flowing like that river. Now, remember the speed limit of the universe. Light speed, c. Imagine you're a fish swimming in this river. Your top swimming speed is c. Far away from the hole, the river of space is flowing slowly. You can easily swim upstream, away from the hole. You're safe. As you get closer, the river speeds up. The gravity is dragging space inward. You have to swim at 50% of light speed just to hold your position, and then you reach a specific line, a line where the river of space is flowing inward at exactly the speed of light. This line is the B event horizon. If you are at this line and you swim upstream at maximum speed, you will stay exactly where you are. You're like a person running on a treadmill that is moving too fast. You're swimming at the speed of light, but the space you're swimming in is falling into the hole at the speed of light. Net speed, 0. And if you cross that line, if you drift just 1 inch inside the event horizon, the river of space is now flowing faster than light. Even if you swim upstream at sea, you will be dragged backward. You will be swept down the waterfall. This is why nothing escapes a black hole. It's not that the gravity is too strong for light to break free. It's that the space containing the light is falling faster than the light can climb. The exit door is moving away from you faster than you can run toward it. This is a terrifying geometry, because once you are inside, all roads lead down. Down is no longer a direction in space. Down becomes your future. Hitting the singularity, the center of the whole, is as inevitable as next Tuesday. You cannot avoid it, just as you cannot avoid tomorrow. But what does this look like from the outside? This is where space-time gets truly ghostly. Remember, gravity slows down time. At the edge of a black hole, the gravity is so intense that time almost stops. Imagine you stay on the spaceship safely far away. You send a brave robot probe to fall into the hole. The probe has a big clock on its back and a blue light that flashes once every second. Tick, tick, tick. You watch through your telescope. As the robot gets closer to the hole, it enters the slow time zone. You see the light flashes start to space out. Tick, 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 tick. The light from the robot also has to climb out of the gravity well. As it climbs, it loses energy. The blue light shifts to red, then deep infrared. The robot starts to fade, and the clock starts to freeze. As the robot hits the event horizon, time dilation becomes infinite. From your perspective, you never see the robot fall in. You see it slow down and stop. It becomes frozen at the very edge of darkness. Its image hangs there, fading, reddening, forever stuck in the final second before destruction. We call this the frozen star effect. To the outside universe, nothing ever truly enters the black hole. History piles up at the door. But what about the robot? What does the robot experience? To the robot, everything is normal. It doesn't feel frozen. It doesn't see its clock stop. It crosses the event horizon without even noticing. There is no sign. There is no wall. It is just empty space. It looks at its watch, and the seconds are ticking by normally. Tick, tick, tick. It looks back at you, and it sees the universe aging rapidly. It sees the stars whirling. It sees the future of the galaxy flashing by in fast forward, because while it fell for a few minutes, millions of years passed outside. The robot falls toward the center, and then the geometry kills it, but not by crushing it, by stretching it. This is called spaghettification. Imagine you're falling feet first. Your feet are slightly closer to the singularity than your head, because gravity gets stronger, very fast near the center. The pull on your feet is millions of times stronger than the pull on your head. The universe pulls your feet away from your head. You're stretched into a long, thin noodle of atoms. Your world line is unraveled. This is the end of the journey for matter. The fabric of space-time becomes so twisted, so steep, that physics as we know it breaks down. The equations simply say, "Here be dragons." But black holes are not just engines of destruction. They are the anchors of the cosmos. Without these super deep valleys to hold things together, galaxies might not exist. At the center of our own Milky Way, there is a giant black hole, Sagittarius A. It is the calm, dark eye of our galactic hurricane. We're all orbiting it right now, so we have seen the extremes. We have seen the flat plains of deep space. We have seen the gentle hills of Earth. And we have seen the bottomless waterfalls of the black holes. It is dynamic, violent, beautiful landscape. And the amazing thing is, we can understand it. We, tiny creatures living on a small rock, have managed to map the curvature of the infinite. But how does this curvature shape the day-to-day universe? How does space-time decide the shape of a galaxy, or the spiral of a solar system? In the next chapter, we're going to look at the architecture of the cosmos. We're going to see how space-time creates order out of chaos. We're going to watch the invisible hand of geometry build a solar system. But for tonight, Be glad you are here. Be glad you're in the Goldilocks zone of gravity. Not so flat that we float away. Not so steep that we are crushed. Just enough curve to hold us. Just enough curve to keep the atmosphere wrapped around us like a blanket. We are nestled in the valley of the earth, and it is a good place to sleep. In the last chapter we stood at the edge of the abyss. We peered into black holes. We watched the river of space flow over the edge of the world, dragging light and time down with it. We saw the destructive power of spacetime, but spacetime is not just a destroyer. It is a creator. It is the invisible architect that built the house we live in. Tonight, we're going to watch the construction of the cosmos. We're going to ask, how did we get here? How did we go from a chaotic, messy cloud of gas to the beautiful clockwork precision of the solar system? How does a curved fabric build a planet? To understand this, we have to go back to the beginning. I want you to imagine the universe shortly after the Big Bang. It is boring. It is just a vast, endless fog of hydrogen and helium gas. No stars, no planets, no galaxies, just a warm, dark mist filling the void. If the universe had been perfectly smooth, it would have stayed that way forever. If every atom was exactly the same distance from every other atom, the gravity would have cancelled out. The sheet of space-time would have remained flat. The universe would have ended as a cold, featureless soup. But the universe was not perfect. There were tiny imperfections, quantum jitters. In some places, there were slightly more atoms than in others. A tiny clump of gas here, a slightly denser pocket there. This is where the geometry starts to work. Imagine our mattress again. Imagine it is covered in a layer of sand. If the sand is perfectly flat, nothing happens. But if you make a tiny pile of sand in one spot, that spot gets heavier, it sinks, it creates a tiny dimple in the mattress. Now, the sand grains nearby feel a slope. They slide down the slope into the pile. The pile gets bigger, the pile gets heavier, the dimple gets deeper. This creates a feedback loop. The deeper the hole, the more matter it attracts. The more matter it attracts, the deeper the hole gets. Gravity is the engine that amplifies inequality. It takes a tiny difference and turns it into a kingdom. Over millions of years, these tiny pockets of gas grew into massive clouds, giant swirling storms of hydrogen, light years wide, and as they got heavy enough, the pressure in the center ignited nuclear fusion. The first stars turned on. The lights of the universe flickered into existence. But this explains the stars. It doesn't explain us. It doesn't explain the planets. And it doesn't explain why everything is spinning. If you look at the solar system, it is suspiciously organized. All the planets orbit in the same direction. All the planets lie on the same flat plane, like a dinner plate. The sun spins in the same direction. Why? Why isn't it a chaotic swarm like a beehive? Why is it a flat disk? The answer lies in the conservation of angular momentum, or, as I like to call it, the pizza dough effect. Imagine a figure skater spinning on the ice. When she has her arms out, she spins slowly. When she pulls her arms in, she spins furiously fast. This is a law of physics. As you shrink, you spin faster. Now, look at our giant cloud of gas. It is shrinking because gravity is pulling it inward, and because the cloud wasn't perfectly still, it had a tiny random drift. As it shrinks, that tiny drift turns into a spin. As it gets smaller and smaller, the spin gets faster and faster. Now, imagine a ball of pizza dough. If you spin it in the air, what happens? The centrifugal force pulls the edges outward. The ball flattens into a disk. This is exactly what happened to our solar system. The spinning cloud of gas flattened out into a pancake. The sun formed in the centre, the bulge of the pizza, and the planets formed from the crumbs left over in the flat crust. This is why the solar system is flat. This is why we can see all the planets in a line across the night sky. We're living in a giant cosmic pizza that was spun into shape by the laws of motion. But spacetime does more than just flatten things. It holds them in that beautiful, delicate dance we call orbit. I want you to visualize the Earth right now. It is flying through the dark at 67,000 miles per hour. That is fast. That is escape velocity. The Earth wants to fly away. It wants to leave the sun and sail off into the empty void, but the sun has created a valley. The Earth is banking around the curve of that valley. It is a perfect stalemate. The Earth is falling toward the sun because of the slope, but it is moving sideways so fast because of the spin that it keeps missing the sun. Orbit is the art of falling and missing. For 4.5 billion years, the Earth has been falling. It has never hit the bottom. Spacetime provides the track, energy provides the speed, and the result is the stable, rhythmic year that governs our lives. But spacetime shapes things on a much grander scale than just planets. It builds the cities of the universe, galaxies. Look at the Milky Way. It is a spiral, a majestic pinwheel of stars. Why does it hold that shape? Because in the centre, deep in the heart, there is a monster, Sagittarius A, a supermassive black hole, 4 million times heavier than the Sun. It creates a gravity well so deep that it anchors the entire galaxy. Billions of stars act like planets orbiting this central drain. But here, the story gets strange. When astronomers looked at galaxies, they noticed something wrong. The stars on the edge were moving too fast. By all rights, they should have flown off into space. There wasn't enough visible matter, stars and gas, to create a gravity well deep enough to hold them. The galaxy should have torn itself apart, but it didn't. The space-time was curving more than it should. This led us to the discovery of dark matter. We realized that there are invisible hills in the universe. There is a mysterious substance that we cannot see, but it has mass. It bends space-time. It surrounds every galaxy like a halo. It digs the gravity well deeper, allowing the fast stars to stay in orbit. We're living in a house made of glass bricks. We can't see the walls, but we know they are there because the roof hasn't collapsed. And if you zoom out even further, to the scale of the entire universe, you see the Sartant cosmic web. The universe looks like a sponge or a neural network. There are long filaments of galaxies, glowing strings of light, stretching across the dark, and between them, vast, empty voids. This structure, this web, is the shape of space-time itself. Matter has flowed down the slopes into the filaments. The voids are the high ground, the hills where matter rolled away. So, when you look up at the night sky, realize that you are not looking at random dots. You're looking at a structure. You're looking at the skeleton of the universe, traced out in light. Space-time is the mold. Matter is the plaster that filled it. And you're a part of this architecture. The atoms in your body were cooked in the hearts of those stars. The planet you stand on was gathered by that gravity. The orbit that gives you summer and winter is a path through that geometry. You're not an observer of the universe. You're a formation of it. You're a localized knot in the fabric, capable of looking back at the rest of the blanket and wondering how it was woven. It creates a feeling of belonging, doesn't it? To know that the force pulling you into your bed is the same force that spins the galaxy. It is the same curve, the same rule, the same fabric. We're all sliding down the same slopes, but there is one last connection we need to make. We have talked about light, we have talked about time, we have talked about gravity, but we haven't fully connected them all together into one final picture. We need to understand how space-time affects the very thing we use to see it. We need to understand how gravity bends light and how it creates illusions in the sky. And we need to return to the question of time. If space-time is a block and the future is already there, do we have free will? Or are we just marbles rolling down a track that was built before we were born? In the next chapter, as we're going to try to answer the unanswerable, we're going to bring it all home. But for tonight, rest in the stability of the disk. You are on a heavy rock, spinning around a warm star, held safe by the curvature of the dark. We learned to see the invisible. We learned that the empty air around us is not empty at all. It is a thick, jelly-like fabric called space-time. We learned that gravity is not a force that pulls you down, but a curvature in that fabric that you slide into. But so far, we have stayed in the shallow end of the pool. We have talked about the Earth. The Earth is heavy to us, but to the universe it is nothing. It is a speck of dust. The dent it makes in space-time is tiny. It is a gentle, grassy slope. Tonight, we're going to leave the shallow end. We're going to swim out into the deep ocean of the cosmos. We're going to visit the heavyweights, the stars, the neutron stars, the monsters. We're going to see what happens when the fabric of reality is pushed to its breaking point. We're going to look at the geometry of this black hole. I want you to imagine space-time as a vast, stretched rubber sheet. This is a classic analogy, but tonight we are going to push it further. Imagine deep space, far away from any galaxy. The sheet is perfectly flat. If you roll a marble across it, it travels in a perfectly straight line forever. This is the flat space-time of special relativity. It is calm. It is simple. Now, let's drop a star onto the sheet. Let's drop our sun. The sun is huge. It weighs 333,000 times as much as the Earth. When it lands on the sheet, it sinks. It creates a deep, wide funnel. The sheet stretches downward, creating a gravity well that extends for billions of miles. The planets, Mercury, Venus, Earth, Mars, are like marbles rolling around the inside of this funnel. They're moving fast enough to keep from falling into the hole, but the curve keeps them trapped in a circle. But even here, near the sun, the curve is smooth. You could fly a spaceship close to the sun, and if your engines were strong enough, you could climb back out of the funnel. The slope is steep, but it is climbable. Now, let's turn up the gravity. Imagine a star that is much, much heavier than the sun, and imagine it dies. It runs out of fuel. It collapses under its own weight. It crushes itself down into a ball only 10 miles wide. This is a neutron star. A teaspoon of this star weighs as much as Mount Everest. If you dropped this ball onto our rubber sheet, it wouldn't just make a funnel. It would make a spike. The fabric would be pinched downward violently. If you stood on the surface of a neutron star, the gravity would be 200 billion times stronger than on Earth. The time dilation we talked about earlier, it is no longer a tiny fraction of a second. If you spent a few years on a neutron star, decades would pass back on Earth. The slope is becoming slippery. The mud of slow time is becoming quicksand, but nature doesn't stop there. What happens if you pile too much mass onto the sheet? What happens if the object is so heavy and so small that the fabric cannot support it? The fabric rips, or, more accurately, it plunges downward infinitely. It creates a bottomless pit, a puncture, a black hole. Tonight, I want to give you a new way to visualize a black hole. Don't think of it as a solid object. It isn't a planet. It isn't a star. It isn't a thing. It is a place where space-time itself is flowing like a waterfall. Imagine a river flowing toward a cliff. As the water gets closest to the edge, it speeds up. At first, the current is slow. You can swim against it. Then it gets faster. You have to swim harder to stay in place. Then it reaches the edge. The water pours over the cliff at a terrifying speed. Einstein's equations suggest that near a black hole, space itself is falling into the hole. Space is flowing like that river. Now, remember the speed limit of the universe, light speed. See, imagine you're a fish swimming in this river. Your top swimming speed is far away from the hole. The river of space is flowing slowly. You can easily swim upstream, away from the hole. You're safe. As you get closer, the river speeds up. The gravity is dragging space inward. You have to swim at 50% of light speed just to hold your position. And then you reach a specific line, a line where the river of space is flowing inward at exactly the speed of light. This line is the event horizon. If you are at this line and you swim upstream at maximum speed, you will stay exactly where you are. You're like a person running on a treadmill that is moving too fast. You're swimming at the speed of light, but the space you're swimming in is falling into the hole at the speed of light. Net speed, 0. And if you cross that line, if you drift just 1 inch inside the event horizon, the river of space is now flowing faster than light. Even if you swim upstream at key, you will be dragged backward. You will be swept down the waterfall. This is why nothing escapes a black hole. It's not that the gravity is too strong for light to break free. It's that the space containing the light is falling faster than the light can climb. The exit door is moving away from you faster than you can run toward it. This is a terrifying geometry, because once you're inside, all roads lead down. Down is no longer a direction in space. Down becomes your future. Hitting the singularity, the center of the hole, is as inevitable as next Tuesday. You cannot avoid it, just as you cannot avoid tomorrow. But what does this look like from the outside? This is where space-time gets truly ghostly. Remember, gravity slows down time. At the edge of a black hole, the gravity is so intense that time almost stops. Imagine you stay on the spaceship safely far away. You send a brave robot probe to fall into the hole. The probe has a big clock on its back and a blue light that flashes once every second. Tick, tick, tick. You watch through your telescope as the robot gets closer to the hole. It enters the slow time zone. You see the light flashes start to space out. Tick, 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 tick. The light from the robot also has to climb out of the gravity well. As it climbs, it loses energy. The blue light shifts to red, then deep infrared. The robot starts to fade, and the clock starts to freeze. As the robot hits the event horizon, time dilation becomes infinite. From your perspective, you never see the robot fall in. You see it slow down and stop. It becomes frozen at the very edge of darkness. Its image hangs there, fading, reddening, forever stuck in the final second before destruction. We call this the frozen star effect. To the outside universe, nothing ever truly enters the black hole. History piles up at the door, But what about the robot? What does the robot experience? To the robot, everything is normal. It doesn't feel frozen. It doesn't see its clock stop. It crosses the event horizon without even noticing. There is no sign. There is no wall. It is just empty space. It looks at its watch, and the seconds are ticking by normally. Tick, tick, tick. It looks back at you, and it sees the universe aging rapidly. It sees the stars whirling. It sees the future of the galaxy flashing by in fast forward, because while it fell for a few minutes, millions of years passed outside. The robot falls toward the center, and then the geometry kills it, but not by crushing it, by stretching it. This is called spaghettification. Imagine you're falling feet first. Your feet are slightly closer to the singularity than your head, because gravity gets stronger very fast near the center. The pull on your feet is millions of times stronger than the pull on your head. The universe pulls your feet away from your head. You're stretched into a long, thin noodle of atoms. Your world line is unraveled. This is the end of the journey for matter. The fabric of space-time becomes so twisted, so steep, that physics as we know it breaks down. The equations simply say, "Here be dragons." But black holes are not just engines of destruction. They are the anchors of the cosmos. Without these super deep valleys to hold things together, galaxies might not exist. At the center of our own Milky Way, there is a giant black hole, Sagittarius A. It is the calm, dark eye of our galactic hurricane. We are all orbiting it right now. So, we have seen the extremes. We have seen the flat plains of deep space. We have seen the gentle hills of Earth. And we have seen the bottomless waterfalls of the black holes. It is a dynamic, violent, beautiful landscape. And the amazing thing is, we can understand it. We, tiny creatures living on a small rock, have managed to map the curvature of the infinite. But how does this curvature shape the day-to-day universe? How does space-time decide the shape of a galaxy, or the spiral of a solar system? In the next chapter, we're going to look at the architecture of the cosmos. We're going to see how space-time creates order out of chaos. We're going to watch the invisible hand of geometry build a solar system. But for tonight, be glad you are here. Be glad you're in the Goldilocks zone of gravity. Not so flat that we float away. Not so steep that we are crushed. Just enough curve to hold us. Just enough curve to keep the atmosphere wrapped around us like a blanket. We are nestled in the valley of the earth, and it is a good place to sleep. We have arrived, the final leg of our journey together. We've travelled a long way without ever leaving the room. We started with a simple question about a box and a river. We walked through the hall of mirrors that is special relativity. We drove the car of space-time at the speed of light. We slid down the gravity wells of stars and hovered at the edge of black holes. We've taken the universe apart piece by piece to see the clockwork underneath. But tonight, we have to put it back together. Tonight is not about learning a new theory. It is not about bending your brain around a new paradox. Tonight is about integration. It is about taking all these vast, terrifying, beautiful concepts and bringing them back down to the scale of your pillow. I want you to close your eyes. For the last time, feel the room around you. 14 chapters ago, this room felt empty. It felt like a passive container. But now, I hope you feel the texture of it. You're not lying in empty space. You are floating in a rich, four-dimensional fluid. The air between you and the wall is not nothing. It is the fabric of reality. It is the same fabric that holds the galaxies together. It is the same fabric that ripples when two black holes collide 1 billion light years away. And you are not just an observer in this fabric, you are a participant. Feel the weight of your body on the mattress. Do not feel it as a downward pull. Feel it as a connection. The earth, the massive ancient rock beneath your floor, is curving the universe around you. It is creating a gentle valley in the geometry of the dark. Your body wants to slide into that valley. It wants to merge with the slow time of the core. But the bed holds you up. The electrons in the sheets are pushing back against the curvature of space-time. This sensation, this pressure on your back, is the sensation of being held. It is the universe cradling you in its geometry. You're exactly where the math says you should be. You're in equilibrium. Now, think about your breath. Inhale, exhale. That took about 3 seconds. In those 3 seconds, you travelled. You travelled 558,000 miles through the dimension of time. You're not static. You're a traveller. Even while you lie perfectly still, you're hurtling toward tomorrow at the speed of light. You're a comet of consciousness, blazing a trail through the block universe. Visualize your world line. See that long glowing thread that stretches back to your birth. It weaves through the cities you have lived in. It tangles with the threads of the people you have loved. And right now, in this quiet room, your thread is growing straight and true. It is climbing the mountain of time. You're building the future just by existing. But let's zoom out. Let's take one final look at the ship we're sailing on. I want you to imagine your roof dissolving. Imagine the ceiling fading away, revealing the night sky. You see the moon. It looks like a calm white disk. But you know the truth now. You see the invisible funnel of gravity that surrounds it. You see the tides of the earth reaching up to touch it. You see it falling around us, caught in the eternal dance of the falling and missing. Zoom out further. See the earth itself, a blue marble, spinning in the dark. It is moving at 67,000 miles per hour around the sun. But you don't feel the wind. You don't feel the speed, because space-time is carrying you. The principle of relativity protects you. It wraps you in a bubble of normal. No matter how fast the planet spins, your tea doesn't spill. Your dreams don't shake. You're the center of your own reference frame. Zoom out further. See the solar system, the flat pizza dough disk of planets, spun into shape by the laws of angular momentum. See the sun, a giant gravity well, a deep dimple in the sheet, holding us all safe from the cold void. Zoom out to the galaxy, the Milky Way, a spiral city of 200 billion stars. See the dark matter halo surrounding it, the invisible glass walls that keep the stars from flying away. See the supermassive black hole at the center, the dark anchor, creating the waterfall of space that we all orbit. And finally, zoom out to the cosmic web, the vast filaments of light, the great voids, the structure of space-time itself, stretching out to the edge of the visible universe. You are there. You're in that picture. You're not separate from it. We often feel small when we look at the stars. We feel like dust. But physics tells us a different story. Physics tells us that the rules that govern the stars are the same rules that govern the atoms in your hand. The gravity that crushes a star is the same gravity that keeps your blood in your veins. The time dilation that happens near a black hole is the same time dilation that happens when you stand up from a chair. The light that travelled from the Big Bang is the same kind of light that is glowing from your bedside lamp. There is only one universe, and you are made of it. You are a localized knot in the space-time fabric. You are a place where the universe has woken up to look at itself. So, as we come back to the room, back to the breath, I want to address the anxiety of time one last time. We worry about the future. We worry about the past. We worry that time is running out. We worry that we are trapped in the river, being dragged toward a waterfall we cannot see. But remember the block. Remember the crystal. If space-time is a whole, then nothing is ever truly lost. The moments you cherished, the childhood summers, the first loves, the quiet nights, are not gone. They are still there. They are frozen in the amber of the past. They are permanent locations in the geography of existence. You cannot visit them again, because your car only drives east, but they are safe. The past is a library that never burns down, and the future is the road ahead. It may be already paved, or we may be paving it right now, but either way, the view is spectacular. You are the needle on the record. Your job is not to write the music. Your job is to play it. Your job is to experience the melody of the now. So, let go of the steering wheel. You don't need to drive. The laws of physics are driving. Gravity has you. Relativity protects you. The speed of light limits you, but it also connects you. You are exactly where you need to be. Here, in this room, on this planet, in this moment, the only moment that is real for you. Thank you for taking this journey with me. Thank you for looking at the dark and finding the structure within it. The universe is strange. It is bendy. It is heavy. It is fast. But mostly, it is home. You're a traveller of space-time, and you have a long, beautiful world line ahead of you. Sleep well in the fabric.